At the Temple of Jupiter in Baalbek, 50-ton limestone architrave blocks rest atop soaring columns nearly 20 meters above the bedrock. Placing a stone of that magnitude today demands a multi-axle mobile hydraulic crane, substantial outrigger ground prep, and strict operating radiuses to prevent tipping under heavy dynamic loads. Yet Roman site engineers positioned these exact stones using seasoned timber masts, bronze-bushed sheaves, and twisted hemp ropes. This was not the result of tens of thousands of workers dragging stones up vast earthen ramps, nor was it lost ancient mysticism. Classical builders mastered the geometry of mechanical advantage, systematically trading pull distance for multiplied lifting force by routing continuous cordage through compounding pulley blocks and geared capstans. A small crew could safely elevate masses that would buckle uncalculated rigging. The physical proof of this mechanical tradition is cut directly into the surviving stone. Monumental masonry across the Greco-Roman and medieval worlds displays unmistakable rigging points, protruding lifting bosses left for rope slings, recessed U-shaped channels routed into block edges to prevent cordage shearing, and dovetailed Lewis iron mortises cut precisely into top beds to anchor hidden lifting keys. Understanding how ancient master builders engineered these lifts begins with the specific machines that turned muscle into massive vertical thrust. The most elementary mechanical lifter in the Roman arsenal was the Monokolos, a single-spar timber derrick detailed by the Roman military engineer Vitruvius in the 10th book of De Architectura. Rather than relying on a self-supporting geometric frame, the Monokolos channeled massive vertical loads through a single squared mast of seasoned fir or oak, resting on a heavy ground shoe to prevent the base from kicking out under load. To keep this solitary spar upright while under extreme compression, Roman riggers stabilized the masthead with 4 radial stay cables anchored to deeply driven ground stakes or existing structural masonry. The mechanical efficiency of the Monokolos relied on keeping the lifting forces aligned with the timber's longitudinal axis. At the apex of the timber spar, carpenters bound an iron band or fitted heavy bronze eyebolts to secure the top pulley block. A continuous hawser of twisted vegetable fiber, typically hemp or Spanish broom linen, ran from a ground-mounted capstan winch up to the apex sheave, descended to a lower traveling block hooked to the load, and returned to the top fitting. When laborers turned the capstan spokes, the winch converted rotary leverage into linear line pull, while the mast bore the combined downward resultant vector of both the suspended stone and the tensioned haul line. Because the single mast occupied a tiny ground footprint, it excelled in cramped urban building yards where multi-legged cranes could not fit between existing walls. A work crew could erect a Monokolos inside a narrow Roman insular courtyard, run the stay ropes out through window openings to street anchors, and hoist 2-4 wall blocks or lintels straight up 4 stories. However, the machine possessed a critical operating vulnerability: angular instability. The timber mast could only handle loads suspended directly below its apex or within a narrow cone between its guy ropes. If riggers tried to slew the mast laterally or haul a stone inward from outside its vertical plumb line, the uneven side loading introduced severe bending moments across the timber shaft, risking catastrophic splintering or snapping the tensioned guy lines. To overcome the lateral instability of a single mast, classical builders paired 2 timbers into an inverted V shape, creating the bipedal shear legs known to Greek and Roman engineers as the Dikolos. By splaying 2 substantial balks of timber outward at the base and joining them at the apex with a massive transverse iron bolt, the frame eliminated side-to-side sway entirely. The geometric base formed a rigid line of resistance against lateral shearing forces, while the crane relied on just two primary guy ropes running directly forward and backward along its center line of lift. The real operational advantage of the Dikolos was its luffing capability. By paying out or taking in the single rear backstay while maintaining tension on the forestay, operators could pivot the entire frame backward and forward on its footings. This dynamic equilibrium allowed the masthead to reach out beyond the foundation edge, hook onto a newly arrived stone block from an ox cart, elevate it clear of the ground, and then lean inward to set the stone precisely onto the rising wall plane. The load path traveled purely in compression straight down both timber legs into bedrock mortises, effectively doubling the crane working capacity compared to a single spar. Archaeological investigations at 5th century BCE Greek sanctuary sites preserve direct physical evidence of these shear leg machines in action. Along the foundation terraces of the Parthenon on the Athenian Acropolis, excavators identified rock-cut socket cuttings spaced at regular intervals along the stylobate. These paired rectangular mortises held the timber crane feet and anchor stakes securely in the limestone bedrock, preventing the splayed legs from spreading outward under the multi-ton thrust generated while setting the peripteral column drums. Using these calibrated frames, Athenian stonemasons lifted drums weighing between 6 and 10 tons up through the dense scaffold matrices, controlling their descent down to fractions of an inch to match the delicate internal dowel fittings. While the two-legged shear frame excelled along straight foundation lines, it still required secure ground anchors to hold its backstays under high dynamic tension. On uneven hillside terrain, soft soils, or elevated construction decks where driving deep anchor stakes was impossible, ancient builders turned to the Trikolos, a three-legged tripod crane that created an entirely self-supporting geometric base. By arranging three matched timber balks in a wide triangle and locking their apexes together with a forged bronze ring and central suspension shackle, the Trikolos formed a completely closed structural unit. The mathematical mechanics of this configuration were analyzed extensively by Heron of Alexandria in his treatise Mechanica. Heron illustrated through vector diagrams how any downward load suspended from the central vertex distributed its force purely as axial compression down all three timber legs simultaneously. Unlike the Monokolos or Dikolos, which generated massive overturning moments that had to be arrested by guy cables, the Trikolos neutralized lateral overturning forces within its own triangular footprint. As long as the stone mass remained suspended inside the perimeter drawn between the three ground footings, the machine could not tip over, regardless of foundation shifts or high crosswinds. Rigged with a heavy block and tackle assembly hung straight down from the apex shackle, the tripod hoist became the standard heavy lift tool for erecting monumental monolithic stelae, obelisks, and memorial markers across the Mediterranean basin. A three-legged crane could be erected directly over an in-situ plinth without a single exterior guy rope. Roman road engineers transported modular Trikolos kits on military carts, erecting them over ditch excavations and bridge piers within hours. However, the machine's inherent stability came with a spatial trade-off, because the suspended load was trapped entirely beneath the converging timber triangle. Horizontal reach was severely constrained, making it difficult to shift stones outward without manually walking the heavy timber legs across the site. When ancient projects demanded both massive carrying capacity and unrestricted horizontal translation over an entire work area, master builders framed out the Tetrakolos, a heavy four-column timber gantry. Instead of converging spars, the Tetrakolos utilized four vertical corner posts tied together at the top by longitudinal and transverse timber crossbeams, reinforced at every joint with mortise and tenon cuts, heavy diagonal knee braces, and wrought iron strapping. This created an expansive, open box frame that spanned directly over the active masonry course. Inside this overhead rectangular carriage, Roman engineers mounted longitudinal running beams fitted with iron tracks or greased hardwood runners. Suspended from this overhead array was a traveling trolley bearing the main tackle. By coordinating lines from side-mounted winches, operators could elevate a massive stone capital completely off the ground and travel the load along two perpendicular axes, moving it smoothly forward, backward, left, or right while suspended in midair. This dual-axis control allowed masons to lower delicate, carved Corinthian capitals directly onto column shafts without the swinging impacts that regularly chipped stone edges when using guide derricks. The structural sophistication of these timber gantry systems is preserved in the monumental masonry of the Porta Nigra, the surviving 2nd century Roman city gate in Trier. To construct the twin multi-story towers from sandstone blocks weighing up to 6 tons without using wet mortar, Roman stonecutters relied on perfect horizontal alignment under dry joint conditions. Archaeological surveys of the upper tower levels revealed timber beam pockets cut into the interior ashlar faces, marking the exact positions where the 4-column gantry frames climbed alongside the rising stone walls. The Tetrakolos allowed the builders to position hundreds of monumental ashlar blocks in rapid sequence, delivering industrial-scale throughput while keeping the entire lifting mechanism supported by the very walls it was constructing. While 4 post-timber gantries solved the challenge of setting stones within tight horizontal tolerances, the true mechanical engine driving classical construction was the compound pulley assembly. The foundational unit of this rigging revolution was the Trispastos, a 3-sheave tackle system documented by Vitruvius that transformed manual labor into predictable mechanical advantage. The configuration relied on a fixed upper block containing 2 bronze pulleys and a traveling lower block housing a single pulley attached directly to the stone. By threading a continuous line of hemp rope through these 3 rotating wheels, the theoretical mechanical advantage doubled the input force, giving 2 hauling workers the ability to raise 3 times the load they could manage through dead weight lifting alone. In practical experimental tests reconstructing ancient tackle, this theoretical 3-to-1 ratio was heavily degraded by friction. Early cast bronze sheaves rotated directly around stationary iron pins lubricated with animal tallow. Every time the cordage bent under tension across a sheave, internal friction within the twisted plant fibers and sliding friction against the bronze groove absorbed a portion of the hauling energy. When measuring a standard 3-pulley assembly, frictional resistance typically consumed roughly 15 to 20% of the total hauling effort. To overcome this parasitic drag and lift a 400-kilogram limestone block, 2 operators turning an attached manual windlass had to exert approximately 150 kilograms of continuous line pull, translating to 75 kilograms of effort per worker at the winch handles. This physical balance made the Trispastos the supreme rapid deployment hoist of the Hellenistic building boom. The mechanical gain was modest, but it came with a crucial operational advantage: speed. Because the line ratio was relatively low, workers only needed to reel in 3 meters of cordage to raise the load by 1 meter. In the dense urban centers of Pergamon and Priene, where city walls, residential terraces, and small colonnades demanded the continuous placement of 1 to 2-man stone blocks weighing between 200 and 500 kilograms, the Trispastos maintained an unmatched pace. The crew could hoist, position, and unhook a finished ashlar block every few minutes, keeping master masons continuously supplied without stalling the assembly line. When public architecture demanded lintels and column drums weighing upwards of 1,500 kilograms, the 3-pulley system reached its physical limit. Roman engineers met this challenge by scaling the tackle assembly into the Pentaspastos, a 5-sheave compound machine that fundamentally changed how dynamic forces were distributed across timber housings and cordage lines. Rather than relying on simple hooks or single pins, the Pentaspastos housed its sheaves within heavy blocks sculpted from seasoned ash or home oak, woods selected specifically for their exceptional resistance to splitting along the grain under intense compressive stress. Archaeological recoveries from the submerged Roman harbor installations at Caesarea Maritima reveal the internal mechanics of these 5 pulley housings. The upper fixed block held 3 bronze sheaves aligned on a single heavy axle pin, while the lower traveling block contained 2 matching sheaves. Reeving the hoisting line through this 5-part assembly split the total suspended mass across 5 distinct rope falls. If a crew hoisted a 1,500-kilogram sandstone pier, no individual strand of the tackle carried more than 300 kilograms of static tension. This load sharing was critical. It allowed master riggers to operate well within the safe working tensile limit of 30mm twisted hemp line, preventing the dynamic snapping failures that plagued single-line derricks. Operating a 5-pulley hoist required a different ground interface than a simple hand-cranked windlass. With a 5-to-1 line reduction, hauling 5 meters of cordage produced just 1 meter of vertical rise. To handle the increased line speed and continuous torque demands, Roman engineers coupled the Pentaspastos directly to a horizontal capstan anchored into bedrock or heavy timber ground plates. Long wooden capstan bars allowed 4 to 8 men or draft animals to walk in a continuous circle, using their full body mass and leverage against the capstan drum. This mechanical synergy allowed a medium-sized crew to lift massive structural elements smoothly, eliminating the jerking motions that could crack brittle limestone under tension. To hoist the monumental 5-ton architrave blocks that defined imperial Roman civic centers, builders expanded compound tackle to its absolute physical maximum in the Polyspaston. This heavy derrick system did not merely add pulleys, it multiplied them across compound block tiers, pairing multiple multi-sheave housings in tandem to achieve mechanical advantage ratios ranging from 12-to-1 to as high as 24-to-1. At this scale, a single worker leaning into a geared hand winch could exert enough tension to hoist a multi-ton marble lintel straight into the sky, but the extreme multiplication introduced violent structural stresses across every component of the rig. The engineering tolerances of the Polyspaston are visible in the surviving construction records and monumental masonry of the Temple of Trajan in Rome. Erecting the temple's monolithic granite columns and 5-ton entablature blocks required derrick masts carved from seasoned white oak trunks over 40 centimeters in diameter. Under the maximum suspended load of a 5-ton block, the derrick mast operated as a massive vertical compression strut, subjected to immense axial loading combined with severe lateral bending moments caused by the tensioned stay cables anchored hundreds of feet across the construction plaza. The cordage itself represented the primary point of failure. Standard domestic hemp ropes suffered catastrophic fiber shearing when bent tightly around small diameter sheaves under multi-ton loads. For the Polyspaston, Roman builders imported specialized esparto grass cordage from the Iberian Peninsula. Esparto fibers possessed unique elastic properties, yielding under sudden shock loads without snapping and retaining high tensile strength even when subjected to intense internal friction and heating. By distributing the 5-ton dead weight across 12 continuous falls of esparto line, the Polyspaston reduced the tension on the hauling line to just a few hundred kilograms, turning an otherwise impossible megalithic lift into a controlled, repeatable architectural operation. Even with compound pulley ratios exceeding 20-to-1, manual winches and horizontal capstans suffered from a clear human limitation. The amount of muscular force a worker could generate through their arms and shoulders while bracing against the ground. The Romans solved this bottleneck by replacing the winch entirely with the Magna Rota, the giant human treadwheel. By scaling a timber wheel to 4 or 5 meters in diameter and placing workers directly inside its perimeter, the machine converted the continuous downward pull of human body weight into immense rotational torque along a narrow central axle drum. The clearest mechanical window into this device survives in the detailed 1st century relief carving from the tomb of the Hetairai in Rome. The relief depicts a towering derrick crane powered by a massive double-sided treadwheel, with laborers climbing rungs set along the inner rim. As the workers stepped upward, their mass acted at the wheel's maximum radius, several meters from the center of rotation, while the hoisting rope wound around an axle drum with a radius of only 15 to 20 centimeters. This dimensional contrast alone produced an immediate 30-to-1 mechanical advantage before the line even reached the compound pulley blocks hanging from the masthead. When combined with a 2-sheave traveling block, the system delivered an overall mechanical advantage exceeding 60-to-1 without requiring a single metal gear tooth. Operating such enormous stored energy required rigorous mechanical safeguards. If the treadwheel workers lost their footing or slipped under the strain of a suspended 3-ton block, the axle drum would violently reverse, causing the wheel to spin backward at lethal speeds. To prevent backspin disasters, Roman carpenters integrated heavy timber ratchet pawls into the wheel frame. These spring-tensioned wooden dogs dropped continuously behind heavy oak cleats bolted to the wheel's outer rim as it turned. If the crew paused or lost traction, the pawl instantly caught the nearest cleat, locking the entire machine and keeping the multi-ton stone suspended safely in mid-air. Scaling the single treadwheel crane to handle monumental masonry presented a structural dilemma for Roman site architects. While enlarging a single wheel increased leverage, it concentrated tremendous rotational torque onto one side of the timber mast, creating an asymmetric bending moment that threatened to twist the crane off its footing. The Roman engineering solution was the twin-cage double treadwheel gantry, a massive symmetrical apparatus that placed 2 identical 4-meter wooden cages on opposite ends of a shared central horizontal axle drum. This configuration transformed lifting capacity by balancing the mechanical input. Instead of 2 men driving a single wheel, the twin-cage machine accommodated 4 to 8 trained treaders, divided equally between the 2 rims. As the crews stepped forward in unison, their combined body mass applied equal, mirrored downward force along the outer extremities of the axle. This distributed load cancelled out lateral torque across the crane frame, routing pure rotational force directly into the central winding barrel where the primary hoist cable was spooled. The practical execution of this design is visible in the construction of the Pont du Gard aqueduct in southern France. To hoist the monumental Shelley limestone ashlars of the main river arches, blocks weighing up to 6 metric tons had to be lifted nearly 50 meters above the Garden Valley floor without mortar. Lifting stones of that scale to such heights required constant, smooth vertical acceleration. Any sudden jerk or mechanical stutter risked snapping the hemp, rigging or cracking the unmortared stone voussoirs already positioned on the centering frames. Operating the twin-cage gantry required strict coordination. A foreman positioned on the staging deck directed the treaders using acoustic signals, typically rhythmic whistles or hand clappers, ensuring that the men in both cages matched their stepping cadence precisely. If one side climbed faster than the other, the axle would experience uneven shear stress, inducing microscopic slip in the rope coils on the central drum. When properly synchronized, 4 men generating a combined sustained effort of approximately 300 watts could raise a 6-ton limestone block at a steady rate of several meters per minute. Because the lifting forces were immense, anchoring the double treadwheel gantry demanded complex rigging geometry. Heavy stays made from twisted esparto grass or multi-ply hemp lines extended backward and laterally from the masthead to ground anchored deadmen. Roman riggers calibrated the tension on these guy lines using block and tackle luffing tackles to match the shifting center of gravity as the load moved from ground level to the aqueduct's highest arcade. By locking the crane frame in strict compression against the bedrock, the twin cage machine converted pure gravitational ballast into vertical lifting capacity with remarkable structural stability. While human treadwheels dominated open-air civil infrastructure, Hellenistic mechanicians sought to eliminate reliance on sheer human mass altogether by exploring gear-driven mechanical advantage. The theoretical zenith of this approach appeared in Alexandria during the 1st century, documented in the surviving Arabic translation of Heron of Alexandria's Mechanica. Heron introduced a machine known as the Baroulkos, or weight carrier, designed to demonstrate how a solitary operator exerting minimal force could lift an enormous mass of 1,000 talents, roughly 26 metric tons, through sequential gear reduction. The Baroulkos discarded compound pulleys and towering shear legs in favor of a rigid timber gearbox housing 4 interlocking, parallel axle stages. The input began with an iron hand crank driving a primary pinion gear with 4 teeth. This pinion meshed into a secondary wooden cogwheel containing 20 teeth, creating an immediate 5-to-1 reduction ratio. Fixed along the same axle as this second gear was another 4-tooth pinion, which engaged a third cogwheel of 20 teeth. Repeating this gear pairing across 4 successive stages compounded the mechanical multiplication geometrically. By multiplying the sequential gear ratios across all 4 axles, Heron calculated a theoretical force advantage exceeding 200-to-1. A single laborer applying just 30 pounds of manual effort to the operating crank could theoretically produce several tons of line pull on the final winding drum. In mathematical terms, the Baroulkos proved that physical human strength was no longer the primary constraint in lifting heavy weights. Any load could be hoisted given sufficient gear reduction. Yet translating Heron's theoretical mathematics into a functional heavy stone hoist revealed the brutal material limits of antiquity. The primary vulnerability lay in the concentrated shear stresses acting on individual gear teeth. Unlike modern hardened steel gears, Greco-Roman gearing relied on dense hardwoods like boxwood, oak, or cast bronze alloys. At the high torque end of the train, where the final pinion engaged the drum gear, the entire multi-ton load rested upon just 1 or 2 interlocking teeth at any given microsecond. Under dynamic shock loads, such as a suspended marble lintel shifting in its sling, these timber or bronze teeth experienced catastrophic point load pressures that easily sheared grain structures or bent cast metal pins. Furthermore, without low-friction rolling bearings, the cumulative surface friction of 4 rotating axles under heavy load consumed up to 40% of the input energy. While the Baroulkos stood as a revolutionary milestone in gear train engineering, its real-world construction use remained restricted to delicate positioning winches, proving that theoretical mechanical advantage is always bounded by the sheer strength of its materials. To overcome the tooth shear vulnerabilities and backspin hazards inherent in standard spur gear reduction, Hellenistic engineers turned to the geometry of the endless screw. The development of the worm gear, traditionally attributed to Archimedes of Syracuse in the 3rd century before the Common Era, introduced a fundamentally different mechanical interface to ancient hoisting. By meshing a helical screw directly with the teeth of a spur wheel, ancient winches achieved extraordinary torque multiplication within a single, highly compact mechanism. The underlying physics of the worm and wheel winch rely on continuous inclined plane action. As the operator turns the horizontal worm screw via a hand crank, the spiral thread advances through the teeth of the vertical gear wheel. For every full 360-degree rotation of the screw, the driven gear advances by only a single tooth pitch. If the driven gear features 30 teeth, the mechanism delivers an immediate 30-to-1 reduction ratio in a single stage, eliminating the need for sprawling trains of multiple axles and pinions. Beyond raw power multiplication, the defining advantage of the Archimedean worm gear was its inherent self-locking capability. In standard spur gear winches or direct drum tackles, a suspended stone exerts reverse torque that will spin the mechanism backward if the input force fails. In a worm drive hoist, however, the helix angle of the screw thread is shallower than the static friction angle of bronze and seasoned hardwood. While the screw can easily turn the gear wheel, reverse force applied by the load onto the wheel cannot turn the screw. The friction along the helical thread instantly jams the gear in place, providing absolute safety against falling loads without requiring external ratchet pawls. The real-world power of this mechanism was famously recorded by the ancient writer Athenaeus, describing Archimedes launching the Syracusa, a colossal transport ship displacing over 4,000 tons. Built under the orders of King Heron II, the vessel had become stranded on the slipway due to immense hull-to-timber friction. Archimedes designed a multi-stage worm screw winch apparatus operated by a single person, successfully drawing the massive hull down the launching ramp into the harbor. This naval dry dock technology migrated directly into heavy architectural hoisting. Roman harbor engineers adapted Archimedean winches to beach multi-oared polyremes and lift massive granite blocks onto waterfront quays. The worm gear's ability to hold suspended monoliths motionless allowed stonemasons to precisely adjust bedding mortar and align dowel sockets with millimeter precision, transforming dangerous dynamic lifts into controlled, static structural placements. Before a crane could hoist a monumental stone into an architectural facade, ancient builders faced the equally grueling challenge of overland transport. Moving monolithic column drums from distant quarries across soft, shifting terrain often posed a greater engineering hurdle than the vertical lift itself. When the Greek architect Chersiphron and his son Metagenes commenced construction on the archaic temple of Artemis at Ephesus around 550 before the Common Era, the site presented a logistical crisis. The 40-ton marble column shafts had to traverse 8 miles of marshy, alluvial floodplain where standard wheeled carts would sink to their axles. Rather than attempting to construct carts of unprecedented width and wheel diameter, Chersiphron completely inverted the problem. As documented by Vitruvius and later Pliny the Elder, the architect decided to turn the stone column itself into the wheel. Instead of placing the stone upon a vehicle, Chersiphron built a massive timber frame enclosing the column drum, transforming the monolithic cylinder into an oversized rolling roller. To achieve this, masons bored deep circular sockets into the exact center of each end of the marble column drum. Heavy iron pivots were driven into these holes and secured with molten lead to prevent looseness under load. Chersiphron then constructed a stout 4-sided frame of 4-inch oak timbers surrounding the drum. Large bronze journal bearings were mounted into the longitudinal frame members, fitting snugly over the stone's protruding iron pivot pins. When oxen were yoked to the outer timber tongue, pulling the frame forward caused the marble column to rotate smoothly within its bronze bearings, rolling directly over the earth. This rolling drum system dramatically reduced rolling resistance. By spreading the 40-ton mass across the broad surface area of the entire stone cylinder, Chersiphron prevented the localized ground shearing that swallowed traditional narrow wooden wagon wheels. The large diameter of the column drum, often exceeding 1.5 meters, easily traversed small stones and undulations in the roadbed that would have snapped heavy wooden axles. When the rolling monoliths arrived at the marshy Ephesus sanctuary site, Chersiphron integrated the transport frames with low-angle ramp winching systems. Ground-anchored windlasses pulled the rolling drums up shallow timber causeways to the temple platform. Once positioned over their intended footings, masons unbolted the outer timber frame, removed the iron pivot pins from the end sockets, and prepared the stones for vertical placement. By converting the column drum itself into the primary mechanical rolling element, Chersiphron bridged the gap between quarry logistics and monumental hoisting. While cylindrical column drums could serve as their own wheels, the rectangular architraves of the Temple of Artemis presented a far more punishing mechanical problem. These horizontal stone beams were massive monolithic prisms, often exceeding 8 meters in length and weighing upwards of 25 to 30 tons. Dragging them flat on timber sledges across the alluvial plains of Ephesus would have generated insurmountable friction and sheared roadbeds immediately. Chersiphron's son, Metagenes, solved the geometric challenge by enclosing each rectangular lintel inside an artificial timber wheel assembly. Rather than carving the stone into a cylinder, carpenters built 2 colossal wooden wheels, roughly 4 meters in diameter, directly around the opposing ends of the stone beam. Heavy radial spokes clamped around the squared stone, securing it so that the architrave itself became the structural axle connecting the 2 wooden rims. By pivoting the stone inside this timber cage, oxen could roll the massive rectangular monolith over the marshy ground with the same reduced rolling resistance Chersiphron had achieved with the columns. The true engineering challenge, however, was transitioning from horizontal rolling to vertical placement atop columns over 12 meters high. Traditional crane masts of the 6th century before the Common Era lacked the bending strength to hoist a 30-ton point load safely. Metagenes therefore turned to a staged parbuckling and ramp system. Work crews built wide, gently sloping earthen and timber embankments leading to the top of the column peristyle. By wrapping heavy hemp hauling cables under and over the exterior timber wheels of the architrave assembly, teams of men and draft animals winched the enclosed lintels up the ramps. The parbuckling configuration cut the required pulling force in half, functioning as a rolling pulley where the stone acted as its own traveling block. Once the architrave arrived directly above the column capitals, Metagenes faced the delicate task of lowering the stone onto the abaci without shattering the brittle marble through uneven impact. He deployed a sandbox subsidence mechanism beneath the lintel. Large timber cribs packed with fine, dry sea sand supported the weight of the stone above the columns. Masons then unplugged small bung holes drilled into the base of the timber boxes. As workmen raked the flowing sand evenly from all 4 corners, the volume inside the boxes decreased uniformly, allowing the multi-ton architrave to descend millimeter by millimeter onto the column heads. This pneumatic-like hydraulic descent eliminated sudden dynamic shocks that would have fractured the stone capitals, achieving a degree of placement precision that pure rope tackle could not deliver. Once monumental masonry reached the job site, builders needed an unyielding connection between the lifting rope and the stone itself. Ropes wrapped around the outside of a block prevented masons from sliding it flush against adjacent stones, while carving temporary lifting bosses wasted valuable stone and required hours of secondary dressing. Classical engineers solved this with the 3-piece Lewis iron, an internal expanding friction anchor that gripped the stone from inside a hidden mortise. Controlled engineering stress tests on reconstructed Roman bronze and iron Lewis assemblies revealed the precise mechanical principles that allowed a tool weighing only a few kilograms to hoist limestone blocks exceeding 5 tons. The system relies entirely on geometry and lateral force distribution. Masons chiseled a specialized dovetailed mortise into the exact center of gravity on the upper face of the block. The cavity was cut narrow at the top opening and flared wider toward the bottom. To assemble the clamp, the mason first inserted 2 wedge-shaped outer iron arms into the opening, sliding them outward so their angled exterior faces matched the flared undercuts of the stone mortise. A straight, rectangular iron spacer pin was then driven down the center between the 2 wedges, locking them firmly against the mortise walls and preventing them from collapsing inward. Finally, a bronze or iron shackle was placed over the protruding eyelets of all three pieces, and a cross bolt secured the assembly to the crane's hoisting tackle. When the crane applied vertical tension to the shackle, the Lewis iron acted as a self-energizing mechanical clamp. The upward pull drew the central pin, and the tapered outer wedges upward against the converging stone ceiling of the mortise. This vertical hoist force was immediately converted into immense lateral compressive thrust against the solid interior body of the stone. Because limestone and granite possess extraordinary compressive strength compared to their relatively weak shear resistance, directing this expanding force inward allowed the stone to support the entire dynamic load without pulling out or spalling. Once the block was seated flush into the masonry wall, releasing the cable tension instantly unloaded the lateral friction. The mason simply pulled the cross bolt, extracted the central spacer pin, collapsed the two outer wedges inward, and lifted the entire iron assembly out of the mortise, leaving the surrounding stone pristine and ready for the next course. While the three-piece Lewis iron offered an exceptional grip for finely finished architectural blocks, preparing a precision-cut dovetailed mortise into the center of every stone consumed significant mason labor. For high-throughput infrastructure projects where speed was paramount, Roman engineers relied on an alternative lifting mechanism known as the forfex or scissor tongs. Where the Lewis operated internally through expanding lateral compression, the forfex clamped the block externally through contracting scissor linkage mechanics. The forfex consisted of two heavy wrought iron arms crossed and secured by a central pivot bolt, resembling a pair of giant blacksmith shears. The upper ends of the arms terminated in eyelets connected to the crane tackle by short bridle chains, while the lower jaws curved inward into hardened iron spurs or broad gripping pads. Work crews carved two small, shallow dimples into opposing vertical faces of the stone block, slightly above its center of gravity. When the crane operator lowered the open tongs over the stone, the spurs engaged these shallow depressions. As the hoisting rope grew taut, the upward tension on the bridle chains pulled the upper handles together. Because the arms pivoted across the central bolt, pulling the top handles inward forced the lower jaws to close with proportional mechanical leverage, driving the hardened spurs deep into the pre-carved notches. The mechanical trade-off between the two systems governed their distinct archaeological distributions. The Lewis iron required deeper carving but directed all stress into the core of the stone, making it safe for brittle marbles and complex friezes. The forfex, conversely, concentrated massive mechanical shear stresses directly at the outer perimeter of the block. If the crane hoisted with a sudden jerk, or if the stone contained natural cleavage faults near its edges, the localized point pressure from the tongs could shear off the outer stone lip, causing catastrophic drop failures. However, the forfex required only seconds to engage and disengage, needing no spacer pins or locking bolts to be disassembled by hand. Because of this speed advantage, archaeological evidence of scissor tongs appears overwhelmingly in massive, dry-laid defensive walls and underwater civil engineering works. At the Roman harbor complexes of Portus and Ostia Antiqua, hundreds of massive travertine and hydraulic concrete blocks preserve the distinctive conical pinch marks of forfex jaws along their lateral flanks. Harbor workers could swing multi-ton breakwater blocks over the water, lower them into the sea, and instantly release the tongs simply by allowing the bridle chain to go slack, resetting the crane for the next load in a fraction of the time required by internal anchors. While Mediterranean crane development focused on multiplying the number of sheaves in compound pulley blocks, ancient Chinese engineers took a fundamentally different mathematical route to extreme mechanical advantage. Described extensively in the Ming Dynasty technological treatise Changgong Kaiwu and depicted on Han Dynasty tomb reliefs dating back over 2 millennia, the differential windlass, traditionally attributed to the artisan Luban, multiplied lifting force on a single shaft without requiring complex, friction-heavy gear trains. The mechanism consists of two rigidly joined, coaxial wooden drums of slightly differing diameters mounted along a single horizontal axle. Rather than using a single rope that simply winds up, the differential windlass uses a continuous loop of cordage. One end of the rope is anchored to and winds onto the larger drum radius, while the opposing section wraps around a floating, single-sheave traveling block holding the stone load, before running up to anchor onto the smaller drum radius, winding in the opposite direction. When the operators turn the crank handles, the larger drum winds rope in while the smaller drum simultaneously pays rope out at a slightly slower linear rate. The resulting lifting movement is governed entirely by the difference between the two radii. In a single full revolution of the windlass, the length of the suspended rope loop changes only by the difference between the circumferences of the two drums, causing the suspended load to rise by exactly half that difference. If the larger cylinder has a radius of 10 centimeters and the smaller cylinder has a radius of 9 centimeters, one complete turn of the crank displaces only 1 centimeter of total rope loop, raising the stone just half a centimeter. This minute displacement yields a massive theoretical mechanical advantage, calculated as twice the handle radius divided by the difference between the drum radii. This geometry produced an extraordinary practical benefit on ancient construction sites: absolute self-locking stability. Because the tension of the heavy stone block acts equally on both the winding and unwinding sides of the rope loop, the rotational torques applied to the shared axle nearly cancel each other out. The remaining torque differential is so small that natural axle-bearing friction easily overcomes it, completely preventing dangerous dynamic backspin. Chinese builders utilized this compact, ungeared power to lift monolithic stone gateposts, sink heavy foundation cribs, and operate deep vertical brine and salt well hoists, demonstrating how geometric refinement could replace multi-wheeled machinery with a single, highly efficient wooden cylinder. While rotary cylinders solved the problem of steady vertical lift, moving monumental stone across horizontal planes onto high defensive works demanded an entirely different mechanical geometry. Song Dynasty military engineers turned to the physics of the counterbalanced Class 1 lever, transforming the ancient irrigation shaduf into a heavy-duty swiveling crane known as the kele. As documented in the 11th century military treatise Wujing Zongyao, this machine was purpose-built to accelerate the construction of massive tamped earth and cut ashlar fortifications along the Grand Canal network. The kele relied on a massive vertical timber pivot, often a single trunk of seasoned elm or camphor wood, mounted in an iron-collared ground socket that sat within a heavily braced cross-timber base. Atop this central mast sat an asymmetrical rocker arm measuring up to 12 meters in length. The short arm, extending only 2 to 3 meters from the fulcrum, carried an enclosed wooden hopper filled with dense counterweights, adjustable iron pigs, cast lead ingots, or tightly tamped river silt. The long arm reached outward over canal transport barges, terminating in a suspension tackle that hung directly over the cargo holds. By adjusting the mass of the ballast hopper, ancient site managers balanced the system so that an ashlar block weighing 2 to 3 tons exerted only a nominal downward force on the operating crew. Instead of grinding through compound gear trains or hauling against massive friction losses, a ground crew pulled down on guide ropes attached to the long arm to lower the rigging, secured the stone using iron scissor tongs or hemp slings, and then released their downward tension. The counterweighted hopper sank under controlled gravitational pull, snapping the stone upward with minimal manual labor. The decisive advantage of the kele lay in its radial slewing capability. Because the central pivot rotated smoothly through a full 360-degree arc, the crane could lift a stone directly from a moored barge on the canal, swing the load across the shoreline in a single continuous sweep, and deposit it precisely atop an ascending rampart. This radial transfer bypassed the bottleneck of ground-level carting and staging ramps. The structural calculations preserved in song treatises show an acute awareness of bending moments. The main lever was shaped with a parabolic taper, retaining maximum cross-sectional thickness directly over the bronze fulcrum pin where shear stress is concentrated, and tapering toward the working tip to reduce rotational inertia. In high-speed fortification work, batteries of these pivoting levers operated in overlapping arcs along riverbanks, maintaining continuous assembly lines of stone placement that kept pace with imperial logistical networks. Transferring that same radial lifting capability to the water required solving a dangerous physical hazard: the dynamic instability of a floating hull under an eccentric load. In the 4th and 5th centuries, as the Byzantine Empire refortified Constantinople and expanded the massive harbor of Theodosius, naval engineers fitted heavy transport dromons with mast-mounted swivel derricks to unload monumental granite spolia, Proconnesian marble columns, and monolithic basin stones directly onto the quays of the Golden Horn. Excavations at Yenikapı have revealed the structural adaptations built into these maritime workhorses. Unlike a static shore crane, a ship-mounted derrick introduced a shifting center of gravity that threatened to capsize the vessel the moment a multi-ton stone swung outward over the gunwale. Byzantine master shipwrights resolved this through a tri-part stabilization system. First, the crane boom was stepped into a reinforced oak tabernacle bolted directly to the ship keelson, transferring compressive vertical loads into the strongest structural backbone of the hull. Second, heavy hemp stay tackles were rigged from the masthead to iron ring bolts anchored into the granite quay itself, mechanically tethering the ship roll axis to the immovable shore. Inside the hold, an active counterballasting routine unfolded in real time. As a 30-foot marble column was hoisted from the cargo bay by the derrick tackle, crew members rapidly shifted tons of loose beach pebble ballast toward the offshore side of the vessel, countering the listing torque generated by the extended boom. When the timber boom slewed through its 180-degree arc toward the stone wharf, the harbor stay tackles bore the lateral overturning moment, keeping the dromon deck nearly level. This floating derrick design gave Byzantine engineers unprecedented access to the shallowest basins of Constantinople. Heavy freighters loaded with recovered Roman monoliths could moor alongside the quay, swing their booms out across the stone coping, and lower architraves and column shafts directly onto multi-wheeled ox carts without requiring permanent shore-based timber infrastructure. By transforming the ship itself into a counterbalanced crane chassis, the empire moved thousands of tons of imperial architecture across the Aegean and Black Seas and set them seamlessly into place along the waterfront. Yet well before maritime derricks and pivoting masts emerged, prehistoric and Bronze Age builders faced a much more unforgiving engineering boundary, lifting 20 to 40-ton megalithic lintels to heights of 20 feet without any cordage strong enough to bear pure dynamic tension. In ancient Malta at Gigantigia and on the Salisbury Plain at Stonehenge, builders bypassed the tensile limits of primitive natural ropes by relying entirely on the compressive strength of timber through high fulcrum lever tower hoisting. The mechanism operated through alternating harmonic rocking rather than vertical pulling. To raise a massive stone lintel from ground level, workers positioned the stone between the upright support pillars and aligned a primary oak lever beam beneath one end of the monolith. By resting the lever on a low wooden fulcrum and having a crew apply downward body weight to the long arm, the stone was tilted upward by just 5 to 10 centimeters. While that end hung suspended for a few seconds, carpenters packed split timber billets and seasoned oak shims tightly into the newly opened gap beneath the stone, establishing a solid compressive bed. The crew then shifted the lever to the opposite end of the stone, tilted that side upward by the same incremental height, and packed timber cribbing underneath. By alternating ends, the builders constructed a self-supporting timber crib tower directly beneath the megalith as it climbed. This method eliminated the risk of catastrophic drop failure. At no point was the multi-ton block hanging from ropes that could snap or stretch. The load path traveled downward continuously through interlocking timber layers into the bedrock below. As the timber crib rose, the fulcrum itself was systematically raised by adding interlocking layers of horizontal cribbing alongside the tower. Friction was controlled by coating the rocker contact points with tallow or animal fat, allowing the lever to slide smoothly without chewing through the grain of the oak supports. When the stone reached the exact summit of the vertical uprights, workers levered it horizontally across grease-slicked timber cross-members until the mortise hollows carved into the underside of the lintel dropped neatly over the tenon knobs carved into the standing stones. By converting dynamic vertical lift into a step-by-step sequence of micro-levered compressions, ancient builders achieved megalithic elevations using nothing more than seasoned timber beams and gravitational mechanical advantage. While stepped cribbing worked for rough megaliths, classical Greek and Hellenistic monumental architecture demanded absolute surface protection and microscopic joint alignment. Placing a 20-ton entablature onto finely carved column capitals required a mechanism that could halt a suspended load at any millimeter of travel and lower it with micrometer precision. The breakthrough came when Hellenistic engineers adapted the locking mechanisms of military siege engines into architectural lifting gantries. As recorded in the mechanical treatises of Philo of Byzantium, the ratcheted belly winch evolved directly from the spanning systems of the gastrophetes, the ancient mechanical crossbow. In classical warfare, spanning a heavy composite bow required a secure pawl that clicked across a notched iron rack, holding high spring tension so the user could reset their footing without the mechanism snapping backward. Hellenistic builders transferred this principle directly to heavy cordage winches by mounting notched bronze ratchet wheels onto the winding drum axles and seating spring-loaded iron pawls against their teeth. This innovation eliminated the single greatest danger on ancient construction sites: uncontrolled drum backspin caused by sudden worker fatigue or gear failure. As the winch handles turned, the forged iron pawl dropped into each successive tooth valley with an audible metallic click, locking the suspended ashlar block in mid-air at fractional inch increments. If a lifting crew needed to pause to inspect alignment, adjust guide ropes, or clear debris from a column capital, the ratchet held the full dynamic load against the timber crane frame. To seat the stone without chipping delicate carved margins, Philo described a controlled escapement process. The iron pawl was fitted with a weighted tripping lever and secondary braking friction rings. By tapping the release lever while maintaining hand pressure on long wooden brake bars, the crew allowed the ratchet wheel to slip tooth by single tooth. This controlled release lowered the stone at speeds under a millimeter per second. In the construction of Hellenistic theater stage fronts and monumental temples, where marble blocks had to join with seams so tight that a knife blade could not pass between them, the ratcheted winch turned raw hoisting power into a precision instruments workshop, laying the mechanical groundwork for complex classical gearing. While muscle power drove the vast majority of Greco-Roman winches, the deep extraction shafts of the Western Roman provinces pushed human and animal endurance past its mechanical limit. In the copper and silver mines of Rio Tinto in Hispania and the gold workings of Donaghcothi in Wales, shafts reached depths exceeding 300 feet beneath the water table. To lift both waterlogged spoil and dense, multi-ton ore buckets out of these vertical abysses, Roman engineers developed heavy vertical hoisting drums driven entirely by hydraulic power. At the core of this system was a high-torque overshot waterwheel constructed from seasoned oak and Iberian pine, mounted on a squared timber axle that terminated in a heavy winding spool. The fundamental challenge of hydraulic hoisting was directional control. Diverting water to stop a wheel is simple, but reversing a water wheel normally requires draining the system, reversing axle gear engagement, or forcing the entire watercourse into a reverse raceway. Roman engineers solved this by designing bifurcated overhead timber flumes controlled by counterbalanced sluice gates. By shifting a single lever at the shaft head, the operator diverted the water jet from the forward buckets to a secondary set of opposed buckets on the same wheel rim. This reversed the wheel rotation instantaneously under full load without requiring disengagement of the hoisting drum or introducing mechanical backlash into the deep shaft cable. The archaeological evidence preserved in the waterlogged acidic galleries of Rio Tinto reveals pairs of wheels measuring up to 15 feet in diameter, fitted with radial spokes mortised into solid bronze bushed hubs. These wheels did not merely drive scoop pumps to dewater the gallery. Their central axle extended into timber head frames equipped with dual-grooved winding spools. As one heavy leather or kibble descended into the shaft under its own tear weight, acting as a partial counterweight, the ascending loaded kibble was drawn upward along vertical guide timbers anchored directly into the rock face. By converting the potential energy of channeled surface streams into sustained axle torque, a single hydraulic hoist could raise continuous 2-ton loads from the deepest galleries without the mechanical fatigue or structural footprint of a subterranean animal team. Under the wooden floor of the Flavian amphitheater, vertical hoisting operated under an entirely different constraint: instantaneous speed and synchronized delivery. The subterranean hypogeum of the Roman Colosseum was engineered as a multi-tier staging machine containing 28 independent timber elevator shafts, each designed to hoist scenery cages and apex predators directly into the arena through trapdoors in the arena boards. Unlike traditional construction derricks that prioritized high mechanical advantage over lifting rate, the Colosseum elevator utilized a direct vertical guide gantry powered by a network of parallel floor-mounted capstans. Heavy oak uprights, cross-braced with iron straps, were seated directly into travertine foundations cast into the floor of the hypogeum. Inside each vertical timber track ran a framed timber cage, stabilized by bronze-faced sliders that rode inside greased vertical hardwood channels. This prevented the cage from racking or jamming when shifting animal loads created sudden asymmetrical lateral forces. The critical mechanical innovation that made these lifts viable with modest human teams was dynamic counterweighting. Thick hemp ropes ran from the upper corners of each cage over bronze sheaves pinned into the arena floor joists, terminating in heavy suspended baskets loaded with cast lead pigs. By calibrating the lead ballast to match the combined tear weight of the timber cage plus half its anticipated live payload, Roman engineers slashed the net force required to initiate the hoist. 4 men turning a central capstan on the hypogeum floor could accelerate a 600-pound cat or an elaborate stage set 40 feet upward in less than 20 seconds. As the cage reached the ceiling joists, hinged iron catches automatically snapped beneath the base frame to lock the platform level with the arena floor, while an overhead counter lever tripped the trapdoor hinges open. The system integrated dozens of isolated vertical hoists into a single, centrally coordinated theatrical machine, cycling hundreds of lifts in a single afternoon of games. By the early 15th century, the construction of the colossal octagonal dome of Santa Maria del Fiore in Florence presented a hoisting problem that exceeded every surviving Roman timber design. Filippo Brunelleschi needed to elevate more than 37,000 metric tons of sandstone, brick, and marble over 200 feet into the air. Traditional treadwheel cranes were dangerously inefficient at this height, requiring exhausting human shifts, while conventional animal winches wasted critical hours unyoking and reversing draft teams every time the hoisting bucket needed to descend. Brunelleschi resolved this bottleneck by engineering the world's first reversible, 3-speed animal-powered hoist, meticulously documented in the technical sketchbooks of Mariano di Jacopo and Leonardo da Vinci. At the base of the cathedral, two continuously circling oxen turned a vertical main driveshaft in a single, unbroken direction. Mounted along this central shaft were two large horizontal crown gears with their teeth facing each other across an open gap. Positioned between them was a horizontal winding drum shaft tipped with a sliding lantern pinion. The mechanical breakthrough lay in the sliding clutch mechanism. By engaging a heavy iron shifting lever, the crane master could slide the horizontal lantern pinion into mesh with the upper crown gear to wind the hoisting rope upward, or slide it across into mesh with the lower crown gear. Because the lower gear engaged the pinion from the opposite side of the rotational plane, the horizontal drum instantly reversed its rotation, lowering the empty bucket back to the piazza floor, while the oxen continued their steady, forward circular walk. To handle loads ranging from light mortar buckets to colossal 5-ton marble tie beams, Brunelleschi cut 3 distinct step-down gear ratios directly into the axle assembly. By sliding secondary spur gears along splined iron shafts, operators could shift between high-speed light lifting and maximum mechanical torque without stopping the draft animals. Brunelleschi's reversible ox hoist operated continuously for over a decade, completing thousands of high-altitude hoisting cycles without a single catastrophic cordage or gearbox failure. When modern engineers analyze ancient lifting, the ultimate benchmark remains the monumental Roman podium at Baalbek in modern Lebanon. Here, the Temple of Jupiter sits atop the trilithon, 3 colossal limestone blocks, each measuring over 62 feet in length, 14 feet in height, and 12 feet in depth, weighing upwards of 800 metric tons apiece. Hoisting a single monolithic mass of this scale 23 feet above the bedrock foundation appears to defy classical timber mechanics, leading to persistent claims that ancient cranes were incapable of the feat. The structural and archaeological calculations of Jean-Pierre Adam reveal precisely how Roman engineers solved it using distributed shear leg physics. No single ancient crane could survive 800 tons of tension. Seasoned oak shear legs and hemp cable assemblies of standard classical dimensions hit physical shear and tensile failure limits far below that threshold. Instead of relying on a single mega crane, the Romans assembled a synchronized array of 16 parallel shear leg frames, positioned side by side along the podium perimeter. Each timber derrick was rigged with multiple sheave pulley blocks containing up to 12 bronze pulleys apiece, dividing the total 800-ton deadweight into manageable distributed loads of 50 tons per timber gantry, and further reducing the line tension on individual hemp hawsers to roughly 2 tons. Primary mechanical hurdle was not raw capacity but capstan synchronization. To prevent uneven line loading, which would concentrate the mass onto a single frame and trigger a progressive structural collapse, Roman site masters coordinated 16 separate 4-spoke capstans installed across the terrace. Over 800 men and dozens of draft oxen turned the capstans in unison, guided by rhythmic acoustic signals. Unlike modern 1,000-ton hydraulic mobile cranes, which must concentrate astronomical ground-bearing pressures onto 4 small outrigger pads, the Roman timber array distributed the megalith's weight across a broad geometric footprint of dozens of timber footings. By replacing concentrated mechanical brute force with mathematically synchronized timber distribution, Roman builders seated the largest cut stones in human history without exceeding the yield strength of ordinary wood and cordage. Across the evolution of these 24 lifting machines, from archaic Greek single-mast shear legs and Roman compound treadwheels to Song dynasty slewing cranes and Renaissance multi-speed transmissions, historical builders mastered every fundamental geometric principle of mechanical advantage. By compounding simple machines, manipulating lever arms, and rigging multi-sheave block and tackle systems, master builders proved that theoretical hoisting power could be amplified to practically any required ratio. Yet every machine in this developmental arc operated in constant tension with the physical boundaries of pre-industrial materials science. Increasing gear ratios and adding sheaves brought steep operational penalties, severe frictional drag across tallow-lubricated timber journals, the structural shear limits of hardwood gear teeth under sudden dynamic load, and the vulnerability of vegetable fibers to snap under unyielding deadweights. Rather than attempting to build impossibly massive single timber engines, ancient site masters conquered megalithic construction through geometric distribution, dividing monumental masses across modular gantries, counterweights, and synchronized teams. Which ancient mechanical solution, the sheer mechanical multiplication of the Roman treadwheel or the reversible transmission of the Renaissance ox hoist, displays the more sophisticated grasp of physics? Subscribe to explore deep, evidence-based mechanical breakdowns of lost engineering, classical architecture, and ancient industrial technology. Which ancient mechanical solution, the sheer mechanical multiplication of the Roman treadwheel or the reversible transmission of the Renaissance ox hoist, displays the more sophisticated grasp of physics? Ultimately, ancient heavy lifting was fundamentally limited not by mechanical advantage, which could be multiplied almost infinitely through gearing, but by the tensile failure threshold of organic ropes and the bearing friction of bronze on wood axles.